Assalamu alaikum everyone. In today's lecture, we are going to cover the buckling, okay, how we can perform the buckling analysis in ANSYS. Okay, previously we have covered the effect of self-weight. Okay, we know that what is the buckling, okay. So for that, okay, we know that buckling is basically the instability which occurs when you apply the compression load on slender members, especially on a column buckling. Here you can see the buckling of soda can, okay, due to the applied load. Okay, it's a sideway. When buckling occurs, the body, there is a large deformation, sideway deformation in the body. Okay, why it happens? Because the body lost the stiffness. Okay, it may be in a particular area or in a major area. So we can categorize the buckling on the basis of that. Okay, so that's called the local buckling and the global buckling. For the local buckling, okay, it occurs, you can say that in a very small area. Okay, so meaning, for example, this is the body, and for the body loses stiffness in a small area, then we can call that the local buckling. So in that case, the body still can support the load. Okay, for example, you can see the dents, okay, in a oil can. Okay, there can be dents here, or you can see the local deformation here, but the can still can support further loads. So that would be the local buckling. But you can say that a main buckling or just the buckling, okay, the body loses majority of the stiffness and can no longer support the load. Okay, so it caused the drastic failure of the object. Okay, first of all, if you draw the stress strain or the force displacement diagram for the buckling, okay, you see that then buckling is highly a non-linear phenomena. Okay, you see that as the load increases, the displacement also increases, but at a particular point, okay, that's the maximum point, or you can say that the limit point, there occurs the deformation in the body, and the body cannot resist. Okay, the body loses stiffness. Okay, the body deforms. Okay, you see that the displacement is increases, the body deforms here, but without further increase in force, and the body changes orientation. Okay, let's say that the shape of this beam changes from this curve, changes from this one to this one, and it reaches a point, and then it can further support the load. Okay, this phenomena is called the snap through phenomena, and this also occurs. So it's highly a non-linear process. Okay, so if you solve this non-linear behavior of the object, the buckling behavior, then this can be a really challenging problem, and it's computationally very expensive. So normally you see that there are basically the three ways. Okay, the first one is the linear eigenvalue analysis, which is basically similar to the Euler buckling, because both uses the linear static structural analysis. They uses the material isotropic, and it behaves linearly. So we are in the non-linear buckling analysis, which is basically a little bit complex, and then we have the transient analysis. But today we are going to perform the Euler buckling analysis. Okay, it's basically it avoids the complexity of the non-linear behavior. Okay, it doesn't follow that. Okay, it solves it just stays the analysis within the linear region, and then you can see that it uses the linear set of equation to predict theoretical buckling strength of an ideal elastic structure. Okay, which is basically we determine the critical load. Okay, it's the most efficient method, and in this method we also determine the different modes, okay, of the buckling. Okay, you see that the buckling, the modes mean the different ways, okay, the different shapes the body can obtain during the buckling. Okay, for example, okay, you have a you see that there is a fixed support and there is a pin support. This can be one mode. So you can say that this can be, okay, the S shape. Okay, this is the second mode for the same beam. So these are the modes. Okay, we can determine the different modes, failure modes, and then it doesn't involve further complex analysis. So that's why this is very easy and computationally not expensive, very expensive. So it doesn't give us very accurate result, but it's a very first step, okay, to perform the stability analysis on the body. Okay. So that's why it's eigenvalue method. Okay, whenever we use this method, okay, we are basically concerned. There are two outputs we get. First one is the load multiplier, and then we get the mode shape. Okay, so the load multiplier is not basically the critical load. Okay, we have to multiply this load multiplier with the applied load in the static analysis, and then and the second one is the mode shape. Okay, both we will get that from this analysis. Okay, so if you see that in the buckling in eigenvalue method, okay, this is the actual behavior. So the predicted load is a bit greater than what is the actual load. Okay, so that's why, but we can get an estimate. Okay, a little bit higher, but we can say that this is the first step. Okay, to get an idea. Okay, the buckling analysis we perform in two steps. Okay, first we perform the preload status or analysis, which is basically, it can be a linear or non-linear analysis, and then we perform the buckling analysis. And whatever load we apply in this, okay, this is similar to basically the static structural analysis. Okay, we will perform the static structural analysis, and then we will add the buckling analysis. Okay, and then we can say that the critical load is basically the applied load in the base analysis multiplied the load multiplier. Okay, just keep in mind that whatever load we apply here, it doesn't affect the buckling and critical load. Okay, because at the end you are going to multiply that. Okay, if this load, the base load load in base analysis is higher for a particular failure mode, then the load multiplier will be lower. Okay, and then you can change that. Okay, so let's just jump to the software. Okay, for this analysis I'm going to use the same geometry. Okay, I have previously drawn. Okay, where is that? Let me check it. Where is that? Okay, here it is. Okay, so I'm going to use this one. Okay, the same I-beam section and W1430. Okay, you can get the dimensions from here, and then this is my geometry here. And now you see that I want to apply the buckling load. Okay, that would be perpendicular to this surface, and I use this beam section as a column. So first I need to change the orientation here. Okay, right now the base is in XY plane, so I want to change that to you see that XZ plane. Okay, so that I can apply the load in Z direction. For that you just need to go to the create option, and here there is an option of body transformations, like the move here, and the move type selected to by plane. Okay, so the source plane here is select the XY plane, and then this is our source plane, and for the destination plane I want to move it in XZ plane, so select the XZ plane, and then this is, and for the bodies, okay, select the body. This is my body here, and then where is the body? Select the body, apply, and then you can see that okay, this would be done. Okay, that's what I want to do. So click generate, and now I have my desired you can say that orientation. So let me just close that. Okay, now I need to perform the static structural analysis. Okay, for that I will just go to the select the static structural analysis, just select it here, and then copy paste on just drag it to the geometry. Okay, to the geometry. Okay, now it will take the geometry from here, and then start ANSYS mechanical, and it will take some time. Okay, just wait a bit. Okay, so I have my geometry here in the graphics area. Okay, so for the mesh I would just create the default mesh here. Okay, just let it be, and then okay, for I will fix this one, the bottom face, and then I will apply load at this top face. Okay, so for that, okay, just okay, meshing, then okay, mesh is done. Okay, this is my mesh, and right click here, insert select the fixed port where it's the fixed port, select the face and then the face filter. Okay, oh sorry, I lost. Okay, so I would fix this port here using the right mouse button. I can zoom in and then select this face, apply. Okay, so this face is fixed, and then pressing the H button, it will again shift to the move to the isometric view. Okay, so now on the top face I will apply the load here. So again, the static structure, insert force, select the force, and then select the upper face, apply, and then I will apply a force of 2000 Newton in negative y direction. So component, apply by component, minus 2000 Newton force. Okay, this force, I'm again telling you, this force will not affect the critical load, okay, because if you apply the greater force here, the load multiplier value will decrease, so that will not affect our results. Okay, for the insert option, I will add the total deformation, and then I want to know the stresses as well. Okay, I will because it will deform in the y direction as well, z direction as well, and the x direction as well, it may deform. So that's why I'm using the total deformation and the equivalent stresses here. So right now I will solve my model. Okay, it's almost done. Okay, so I have my results. Okay, this is the deformation, and then these are the equivalent stresses. Okay, that's fine for me. Okay, just now I've done that. Okay, just close it, and this is I say that this is our base analysis. Okay, and right now this is a linear analysis, and based on that I would perform the eigenvalue buckling. Just make sure that यहाँ पे आपने just be careful that you just need to drag it from engineering data, geometry, model, and then the setup. Okay, and then add solutions as well. Okay, so till that, okay, you have configured it. Okay, all the data from this will be transported to this one. Okay, eigenvalue buckling, and then click the setup here. It will again open the ANSYS mechanical. Okay, so here okay, I have the result from the previous solution here. If you go to the analysis setting, it says that maximum modes to find. Okay, so how many modes we are going to find? So just I will increase that to 6 modes or 7. Okay, you can increase it to 10, so I will say that 7 modes, just this one step, and then solution, and then solve. Okay, just wait a bit. Okay, it will, okay, the output will be, as I said, the load multiplier and the number of modes. Okay, so which I have defined here. Okay, the 2 here. Okay, sorry, 7. I have defined I need the information for the 7 modes. Okay, so here is my output. Okay, if you click the solution here, these are my load multipliers. As you can see that, okay, these are the 7 mode multiplier. Now I see that, okay, how many modes we can achieve in this structure. For that, just right click here, just select all these, and then create mode shapes results. Okay, so okay, it will create evaluate the total deformation for all of these. Okay, just click that, and okay, so I have my results. Okay, you see that this is my first mode of deformation, and you see that okay, it will deform. Okay, this shape you will attain, and then you have the second deformation. Okay, it can twist a bit. This is the second mode which is achievable, and this is my third mode, and then you see that these are the local deformation. Okay, you see there, okay, the local buckling. Okay, because the deformation is in this area, and this is all these are okay, but the local deformation will not occur in this case. Okay, because you can see that, okay, these are for the local deformation, the load multipliers are higher. Okay, so first 3 are possible. Okay, the beam can deform in this direction, okay, in this way, but these are not possible. Okay, so that's why these 3 are possible. And then to determine the critical load values, okay, you can just multiply this 263.7 with the 2000. Okay, you see that, then that would be a load multiplier. But you see that, okay, I have defined the force here, so just go to that. Okay, the first is 263.1. so if I change the force value here to, you see that if I decrease that to minus 1000, okay, I will do that, and then I will again solve that, evaluate all results. So you see that, okay, just wait a bit. Okay, just let me clear the previous generators, right? And then, okay, solve it again. Okay, you see that, okay, now I decrease the force to 1000. Okay, so as a result, okay, I decrease the force, and you see that the load multiplier is increased. So if you multiply both these values, so you would get the same load. Okay, this is about today's session. I hope you get that, how you can perform the buckling analysis. Okay, I hope you can do that, and I want you to solve the similar problem and from the book, and compare your results from the ANSYS. Okay, and then critical load. Okay, just multiply these two values. Okay, you would get the results in Newton. Okay, 1000 multiplied by this one. Okay, that's it. Okay, if you have any question, please write in the comment, or you can ask in the class. Thank you.